Hey everyone, in this video we're going to cover the topic of optimization. And so what optimization is taking real life scenarios or applications, word problems, and trying to find the extrema, right? Max and minimum values. So let's look at this example. A farmer with 750 feet of fencing wants to enclose a rectangular area and then divide it into 4 equal pens with fencing parallel to one side of the rectangle. What is the largest possible total area of the 4 pens? So we focus on optimization. You want to ask yourself after you read the problem, and you may have to read it multiple times. I have said that before when we did related rates problems. It's okay to read it multiple times. And so we're focusing on, okay, max and min. So what is it that we want to find? What is it that I want to optimize? And so focus on the question, what is the largest possible total area of the 4 pens? So we're trying to then maximize the area. Area of what? So let's read the problem again. Rectangular area. So that means I want to be able to maximize the area of a rectangle. So let's draw a picture to set up the situation, the scenario that we have going on here. So here we have a rectangle and it's been divided into 4. Pretend that those are equal pens. And so a rectangle usually has length times width, right? The area of a rectangle is length times width. So it doesn't matter which way you divide it. Like I could have said, right, draw my 3 lines lengthwise and say those are the 4 equal pens, but just based on the situation, it kind of makes sense that it goes this way. So you have your 4 equal pens. In the end, your dimensions will come out to be the same. So let's see. So we have our rectangle. I know that the area is length times width, and we have our 4 pens. All right, so what is it that we're trying to do? Maximize the area. So I have here A is length times width, but notice that I have 2 variables. And in order to find the maximum of something, the maximum of a function, what do we have to do? I have to be able to take the derivative and set it equal to 0 and find critical numbers. But can I do that right now? No, because I have 2 variables. So the area, in order for me to find critical numbers, I need to put the area in terms of 1 variable. So how can we get the area in terms of 1 variable? Well, there's stuff I haven't used. Why haven't I used? A farmer with 700 feet of fencing, so I haven't used that yet, wants to enclose a rectangular area and then divide it into 4 equal pens. So I have my picture with fencing parallel to one side of the rectangle. What is the largest possible area? Okay, so what is the largest possible area? I have my area function, area equals length times width, or area formula, but I have 2 variables. So let's use the fencing. I know that fencing is 750 feet. So what does that represent of the rectangle? The units tells me this is a measure of length. So, and fencing is what goes around, right? So that means that this is the perimeter. And our rectangle here is not a standard rectangle. It's not just a 4-sided. Remember, it says we are using the fencing to divide the rectangle into 4 equal pens. So that's why I have the W's in there. So these are being made up by the material, the fencing material that we have available. So that means that then the perimeter for this particular rectangle, this is why the picture is important, is length plus length. So I have 2 of those. So 2L, normally, right, is 2L plus 2W, but in this case we have how many W's? I have this edge, so 1, 2, 3, 4, 5, so plus 5W. So that's the perimeter, and I know that the amount of fencing is 750, so 750 equals 2L plus 5W. And so this equation oftentimes is called a constraint. So a limitation of the problem. So essentially we want to find the maximum area of this rectangle given this constraint, given this limitation. It has to satisfy this criteria. So, but I oftentimes call it the helper equation. My constraint is the helper equation. And why do I call it the helper equation? Because this equation is what's going to help me write the area in terms of one variable. So I'm going to solve for one of them. So I know that area is length times width. So I need to replace either L or W. So I'm gonna solve for L because that just has a 2 in front instead of a 5. So when I divide by 2 is a little bit of a better fraction than if I divide things by 5. But it really doesn't matter which way you choose to, which one you choose to solve for. So I'm going to solve for L, so I'm going to subtract 5W from both sides. So I'm going to have 750 minus 5W equals to L, and then divide both sides by 2. So we're going to have 750 minus 5W over 2 equals L. And so now, right, this is my constraint, my helper equation. This is helping me write the area in terms of one variable. So A is equal to then L. By L, I can replace it with that. So 750 minus 5W over 2 times W. And now I can simplify this. So divide it out. So 750 over 2 minus 5W over 2, and then times W, or distribute the W first, whichever one you choose to do. So my area then is what? So here I'm going to get 375 minus 5/2 W times W and distribute the W. So and notice that now everything is in terms of W. So I'm going to have A of W equals 375W minus 5/2 W squared. So now this is my area formula, and notice that I succeeded in getting it in terms of one variable. So now I can take the derivative. Why do I take the derivative? To find critical numbers, because the critical numbers are where we attain our maxes and mins. So take derivative. So A prime of W will be 375 minus, bring the 2 down, so that cancels with the half, so minus 5W. And then set it equal to 0 and solve for W. So I'm going to have 375 equals 5W, which means divide both sides by 5, so W is 75, or 375 divided by 5. So this is our critical number. That's where the derivative is 0. You could have also, this is a quadratic, so you could just find the vertex as well, and that will give you the maximum. And now here we're going to check, is this, we want to make sure that this is in fact a maximum, right? We're trying to find the largest possible total area, so we want to maximize the area, which maximize the area means verify or find the maximum area. So I only get one critical number, so I want to make sure that this gives me a maximum, because I need to double check it, because what if this is a minimum and then I don't have an answer to my problem. So there are 2 ways that you can check for maximum. So one is the test point method that we've been doing. And so this means you will plug in your critical number, so 75, and this is where the derivative is 0, and then you want to test what is the area function doing. So plug in something smaller than 75, like 70, and then put it in here. So 375 minus 5 times 70, is that positive or is that negative? Which will be positive, right? Because 5 times 7 is 35, so 5 times 70 will be 350, so 375 minus 350 will be positive, which means the first derivative is positive, tells us the function is increasing. So the area function is increasing there, and then on the other side of 75 is likely going to be decreasing, but you should still check it. So pick something bigger than 75, like say 80. So right, so my first test point was when W was 70, and you get 375 minus 350, which is negative, positive, and then pick like 80. And so here you're going to have 375 minus, and then 5 times 80, which is 400, right? 5 times 8 is 40, and so 400, and that's going to give you a negative. So the first derivative is negative, so that means that the function, the area function, is decreasing. So you do have a local max here. So this is a maximum, which is what we were looking for. So that's good. So that is the width. So let's go back to the question. What was it asking us to find? What is the largest possible total area of the 4 pens? Sometimes, so always go back and read the question, because sometimes it may be asking what are the dimensions that will yield the maximum area. So in this case, it's asking what is the actual largest area. So I already have the width gives me the maximum. So I can say, well, W is 75, so then what's L? Now remember, we had solved for L. L was, what was it, 375 minus, where did we have it? We had right here. L is 750 minus 5W over 2, but we had simplified that to 375, then minus 5 halves W. So let's go back to where our L was. So 375 minus 5 halves W. So with W being 75, that means plug it in. So 375 minus 5 halves times 75. And this will give you the L. And then the area is the length times width. So once we have L, we can say L times W. So what is 375 minus 5 times 75 over 2? We get 187.5 for the length. So that means that the area then is the length, 187.5, times the width, which is 75. And so this will be the maximum area, which is 14062.5. So 14,062.5, and this, the units were feet, so this will be feet square. Now you could have also, instead of finding L, you could have gone to the area formula, right? We had our area formula right here. So as soon as we know that our critical number is 75 and it is in fact the maximum, you can just take 75 and plug it in here. 375 times 75 minus 5 halves times 75 square, and you should still get the same value for the area. So this was the first method, is the test point method. The second method to verify that your critical number is a maximum, so check if W equals 75 is a max, is to do the second derivative test. And remember, the second derivative test is when you plug in your critical number into the second derivative. So our first derivative was, what was it, 375 minus 5W. That's our first derivative. So when you take the second derivative, then that's 0 and you get negative 5. So the second derivative doesn't have a W, so that means that at W equals 75, there's nothing to plug in, right? So that means that this is always negative. So that means that the function is always concave down. So that means that at 75, you're going to have an absolute or you're going to have a max. So at W equals 75, because it's concave down, that means you're going to have something like that. So at 75, you're going to have a local max. And so this is in fact what we wanted. And then now you know 75 is your critical number that gives you a max, and then the process will be the same. Either find the length, and this will be especially if you were asked to find the dimensions of the rectangle, but in this case, because we're only asked to find the area, then you can take that 75 and plug it into the final area formula that we simplified. Plug in 75 in there, and then you will get your value, 14,062.5 square feet. And so that will be the maximum area that this farmer can do with 700 feet of fencing and having 4 equal pens. All right, so summarizing optimization, what did we do? So read the problem and read it as many times as you can. But what I want you to focus is what are you being asked to do? This is an optimization problem, so you're going to be trying to find the maximum or the minimum of something. So focus on that. And usually the question is what tells you. So here, what is the largest possible total area? All right, so I want to maximize area in a rectangle. Come up with an equation. What is the area of a rectangle? Oops, we have 2 variables, so I need something to be able to write it in terms of one variable. Why one variable? Because I need to take the derivative and find critical numbers. I can't do that when I have 2 variables. This is not a related rates problem, right? I'm not taking the derivative with respect to some other variables. So we have to write in terms of one variable, and that's when we get our constraint. Okay, 750 feet of fencing. So write your constraint. That is your helper equation, because it's going to help you write the main formula in terms of one variable. Once you have that formula written in terms of one variable, take the derivative, find critical numbers, which means set it equal to 0, and then check your critical numbers to see that in fact you have a max or a min, whichever you're being asked to find. It's important to check that because depending on the function, you may get multiple critical numbers. One is a max and one is a min. And if you're being asked for the max, you want to make sure that you provide the correct one. So how do you check them? You can do the test point method, or you can do the second derivative test. All right, so to summarize that, I put that in your notes. So let me just put it in here to remind ourselves. So here's a summary on solving optimization problems. Read the problem and identify whether we need to maximize or minimize. Some keywords: largest, smallest, most, least. Draw a picture with variables, or describe what your variables represent. So if you're not, sometimes there's no picture that you can draw, but then describe what your variables are. Like if you're calling things X and Y, what do they represent? And then what do we want to do? Maximize or minimize. And what? Volume, area, distance, time, angle, cost. There's so many things that we can do. Write an equation formula for what we want to optimize. So this is the main formula, and then write the constraint or your helper equation to be able to write the main formula in terms of one variable. Take the derivative to find critical numbers, and then use the test point method or the second derivative test to check the critical number for max or min, whatever you're being asked to find. The last thing will be read the problem again just to make sure that you're answering the correct question. Right, like in this one, my question was, what is the largest area? But like I mentioned, it could have said, what are the dimensions that provide the largest area? So you just have to make sure that you answer the question that you're being asked. All right, I'll record a video for the next example.